So this is the Arduino 16 steps sequencer. These two transistors are for the trigger input, so that the sequence plays, and this is the output. So the trigger goes here, and then it goes back to the Arduino. So I have trigger output if I want to trigger something else with the clock from this sequencer, and also I can use an external clock, and these transistors protect the Arduino so that these things are not connected directly to the Arduino, but first they go through the transistors. And here I have an operational amplifier which sets the output range to 1 volt per octave, because I am using an 8-bit pulse width modulation output for the control voltage, and this only has 256 values. So yeah, I'm using this op-amp for that, for the 2 channels, and also because it's a quad op-amp, I'm using the other 2 op-amps for the gates, to buffer the gates, so that the Arduino is not connected directly to the gate output. And this is basically this CD4053, which is basically a digital relay. It switches the pitch bend mode, so for every step I have a switch, this middle switch. If I engage it, I am telling the relay that this step has to use the pitch bend, which is basically another low pass filter, because I'm using one low pass filter for the pulse width modulation to filter the high frequency, and this thing is passing through a different low pass frequency, so it basically interpolates the control voltage, so it doesn't rise directly to the next voltage on the next step, but it has a slope. And I'm using one of these potentiometers to set the amount of pitch bend. And these here are the shift registers. I have 2 shift registers for each row of 16 steps, and they are connected through the Arduino using the SPI protocol. So I can control each step separately if I want. You know, I don't have to go through the steps one by one. And if the step is off, I don't read the voltage from the potentiometer, because this takes 100 microseconds, and I'm just reading if it's on or off with the digital read. So it's really fast, it's like taking 1 microsecond or so, and so you can just skip the off steps without delay, without noticeable delay. And these other 2 shift registers are for the control potentiometers and switches and buttons, which is this last row here. And you can see that although I have 2 shift registers with 8 pins, which makes for 16 inputs, I actually have only 15, because I messed up and made it with 15. But anyway, it's still a lot of inputs to control the sequencer. And so this is the schematics for the front panel. These are the 3 switches that I have. This one enables the step, so if this is on, then Arduino knows that this step is on, and then reads this potentiometer. This is the pitch bend, which goes directly to the CD4053, and this one is for the full gate. Here goes the signal from the shift registers, from the 8 pins from one of the shift registers and 8 from the other, and in total is the 16 steps. And here for the potentiometer I have made this kind of strange schematic, because I could have made it with this diode to be here and without this transistor, and here directly connected to ground, basically like these diodes here. But I found that this produces much more noise. Here I made a schematics to figure out a little bit better the process. So this is the schematics I'm using now. See, this is like a simulation of noise connected to the signal through 1K resistor, and this is the version which the noise, and I'm measuring it here and here, and here the noise is much more present in the signal. This is the part where the control switches and potentiometers are read. Potentiometers which use the same schematic as here. This is a switch, and this is the push button, and I'm using transistors on the switch and the push button as well, because I'm using the same connection to read both the potentiometers and the switch and the push button. I'm reading all of that with one pin of the Arduino, so everything is connected, and that's how it should be made. Because the thing is, if I put the voltage here on one step, this voltage goes through the diode and here, and it could go here, and that would mess up the signal if the current could flow to the ground again. So this transistor basically has another diode here pointing outwards, so it doesn't let the current go to the ground. And also this diode here also prevents it to go back to the shift register from here. So this signal is isolated like that. So this is the schematic for the PCB with the Arduino. These are the two transistors that I'm using to protect the Arduino from the signal from outside. So this is the trigger signal, which triggers the sequencer to do its thing, and these transistors are basically like switches. The thing is that they actually invert the signal, so if this is a rising edge and this is pulled high, and then the transistor, if it's triggered by the rising edge, pulls this to low, it connects it to the ground basically. So this signal here is inverted from this here, but I compensate that in the code with the Arduino, so the sequence is triggered on the falling edge. This is the digital relay switch, the CD4053. The control voltage comes from digital pin 5 and 6 for the Arduino. So this is for the one sequence and this is for the other. It goes through A0 input, and for the other sequence it goes to B0, and A1 is the pitch bend thing which goes through the potentiometer, and it makes a low pass filter with different cutoff frequency, because this has a very high cutoff frequency. It's just to block the pulse width modulation from distorting the output, and this has the function to not only clear the pulse width modulation from the pulses, but also to remove the sharp edges of the CV signal, so it becomes like a pitch bend. Here goes the signal from the sequencer, from the schematic of the panel. This goes directly to the switches, the middle switch, which is for the pitch bend. And if the switch is activated for that step, then for that step this relay connects to A1, and it goes through the pitch bend low pass filter. This is the output thing which scales the output to 1 volt per octave scale with this trimmer, and this is for the two sequences. And by adding this resistor here as part of the feedback loop, I made it so that if you connect it to a potentiometer, so it has, for example, a 10K resistance to ground in the voltage controlled oscillator, for example, and then if this is not part of the feedback loop, then the voltage drops ever so slightly, and if you connect it to another VCO, it drops more, and so it becomes a little bit out of tune. This is the gate output. This is buffered. It comes from the Arduino. It's read through here from the panel, from the panel for each step. It reads if the step is on or not. And then the gate goes out from the Arduino, and the reason for that is to make it so that it's a pulse. So it's not on through the whole step, but it's a pulse. And this is comes from the switch for the full gate. And this diode comes through here, and this is also diodes, and it basically becomes like an OR gate. So if the switch is engaged, it just goes as a full gate, and if it's not, it's just a pulse. So let's go through the code for this sequencer real quick. The basic setup for the code is that I'm using one timer to set up interrupt surface routine, which goes every 500 microseconds. So this is my main timer, and then I am using it for everything, basically, to set the timing for the sequencer every 3 times that the interrupt service routine is executed. Here I have additional counters, and every 3 times it executes, I read the controls. So the controls for the tempo divider, and the other controls that control the sequencer. Every time the interrupt service routine executes, it checks if it's gotten up to the so basically this parameter here is set from the main tempo potentiometer, and every time the interrupt service routine executes, it increases this number, and then this if function compares it to the value set by the potentiometer. And if it's higher, then basically it's time for the next step. So basically this sets the tempo. So the resolution for the tempo is 500 microseconds, so half a millisecond. Actually, the most important thing about the whole sequencer, if it uses pulse width modulation for the control voltage, is that you have to increase the frequency for the pulse width modulation, because by default from the Arduino is like 500 kilohertz or something like 500 hertz, which is extremely low, and it will be modulating the oscillator. The voltage controlled oscillator will actually be frequency modulated by this pulse width. With these things here, I set up and you set prescalers and things, and basically it makes it so that the pulse width modulation frequency is, I think it was 15 kilohertz or 31 kilohertz, something like that. So the maximum, basically. Yeah, I think it's 31 kilohertz. So this is outside the frequency range for the human ear. And also you have the low pass filter in the schematics. This is the low pass filter. And the other important thing is that the pulse width modulation has to be set to phase correct, because it has a couple of modes, and if it's not set to phase correct because by default by the Arduino is set to fast PWM, and this doesn't work well because it has a larger step between 0 and the first value. So you have 256 values, but if it's not set to phase correct, the step between the 0 and the first value is larger than the next steps, and we want all the steps to be exactly the same so that the thing is in tune. So here is the data sheet for the 328p at mega. and basically you have to go through these tables and read which bits to set and which to clear so that it enters the mode for what we want. So these are basically registers which are like switches. So if you flip this switch, so this is 1 byte and these are like 8 switches. If you flip this switch, you enable one function of the chip, and if you flip this another function, and if both are flipped, then it's third function, and you have to read through the tables to find which combination of bits you have to set in order to work like you want. If we want to set up the pulse width modulation to phase correct, we can use this. This is the name of the register, and see, you basically give it this value. So this means that I first clear these bits of the register, the last 3 bits, and then I only set the last one of them. And this is not for the pulse width modulation mode. For this register, the last bit, this sets the prescaler, so this is the frequency for the pulse width modulation, which I also said it's important. And by setting it to 1, the prescaler is no prescaler. So if it's all zeros, there is no clock, so the counter is stopped. And I set it to 1, so this is no prescaling, so we are using the frequency of the processor, which is 16 megahertz. But we have to reach the value 256, so 16 megahertz divided by 256, and this accounts for 65 kilohertz. And then we actually divide it once more because of the phase correct mode, and it becomes 31 kilohertz, because the phase correct mode goes once to count the output compare register, counts once and then counts again on the reverse, and this makes it more accurate. And this part here is just setting up how to read the controls. You know, for example, this is the main tempo, and I read it and I map it through a range, which I find to be useful. But the more interesting thing is, for example, the type of the sequence, to be forward, backward, ping pong, or skip off steps and stuff. And I make it again with mapping the red value 0 to 5, and then here I use the what I have read. This is a switch, which if it's 0, then it goes forward. If it's 1, then it goes backwards. If it's 2, it's ping pong, and if it's 3, it's skipping off steps, and if it's 4, it's random. You have to basically guess how much you have to rotate the potentiometer, because I'm using it as a switch, basically, not as a potentiometer, but as a switch which has 5 values. But it's an easy way to do it, and it works fine. And the interesting thing is that how I set the quantization. So the quantization is basically set by the volt per octave scale. So I'm just reading the potentiometer and map it from 0 to 60. So these are the 60 notes that we have for 5 octaves, and once we have the 0 to 60, when we set the output, so you see here I'm setting the output compare register, which is like analog write, but it's a port manipulation, it's a bit faster. And first I map it from 0 to 60, and then I shift it 2 bits to the left, so the max value here is 60, and here it would be 240. And the reason for that is that we have 256 values, so 240 is in the range. And then we use this part here to scale this value, because 240 and the maximum is 5 volts, so 240 is like 4.7 volts, and this scales it back to 5 volts with this schematics here. And the interesting thing about how to set it to major or minor scale is actually pretty easy. You see here, I make it for 1 octave first. So for 1 octave we have values from 0 to 12, and but if we use all of them, it's basically not in any scale. It's just 12 semitone equal compartment. But we want it to be in a major or minor scale, and the way I did it is just use an array. And for the major scale, it's just so for the C major scale, the 0th note C, we have it in the scale, so I write it here. Then the next note 1, we don't have it, so I write again 0. Then the second, so 1, 0, 1, and this is 2. Number 2 we have it, so I write it here. Number 3 we don't have it, so I write 2 again. And number 4 we have it. Number 5 we have it. And number 6 we don't have it, so I write 5 again. And then number 7 we have it. 7, 8 we don't have it, so I write 7. And so on. And for a minor scale I did the similar thing. So this is overall how the sequencer works. I hope you like it.